Okay, so good evening. So welcome to the talk tonight. And I will be super busy in juggling which hand to use, but hopefully it won't be interrupt anything here. So yeah, I'm Jodie. So now I'm working at DESA. So we are an AI company trying to help the enterprise to do some cool solutions within some deep learning networks. So yeah, so I'm very grateful to have the help from Helen and Lindsay help me to tackle down the problems and give me some cool ideas in the discussion. So should we start? Okay. Yes. Okay. So this is a paper that introduced in the National Europe's Neuros conference. And the reason why I picked this paper is it got the first prize. So that's why I think it should be a cool paper. And actually, it proved to be yes. So I want to introduce this paper, and we will make a little bit details about how the neural network works with the new differential equation, and what's your application of using the ODE now. And by the way, so this paper was written by the team from Professor Duvener and from U of T. They are doing a great job in this theoretical. So I do recommend you have a deep dive later after the talk tonight. So yes, so starting with the topic, we want to get a quick review about what is neural nets. So the neural nets can be understood as a discrete layers. So today we introduce the terms as like state. State can be understood as an output for each layer. So we call your new state and old state. So when we have a neural networks, what we're trying to do is we are learning some function to update the old state ht into the new state ht plus 1. And the function is called f. So this is just a regular neural nets. We have some input x with some weight layers, activations, then you got a new state ht plus 1. Let me get a quick poll. So how many of you here have ever heard about residual neural networks? All right, so I maybe skip this session, right? So yeah, to remind myself, I still want to talk a little bit. So residual neural networks is a superstar introduced 4 years ago. So the thing about the residual neural networks is they're trying to give you a shortcut to skipping some of the layers. And it's just so fantastic. It's like when you're learning the procedures, it was way more efficient than learning the whole f function. So now we have the old state h1, and the residual is another new f. So in the whole residual neural networks, we're trying to estimate the residual function. So far, we have talked about the residual neural networks, but how could we connect residual networks with the Euler's method, or even say the ordinary differential equations? So here's the thing. So let's repeat the function. So the new state equal to the old state plus a residuals. Let me introduce some little bit mathematic trick. So we introduce some constant t. So we introduce t, so t over t is a constant 1. So we have the formula here, and we reformulate it. So this will be ht plus 1 equal to ht plus delta in a function. Does that look familiar to you? So this is actually a single step of Euler's method to solving the ODE, the ordinary differential equation. By the time I read this paper, I totally forgot what is ODE. So I do go Google it. It reminds me of what I learned in the undergrad. So do not be worried about if you doesn't remember ODE. So we will get a review about what you learned from undergrad.
So if you go back to the previous slide.
Yep.
Just a clarification.
Sure.
I think it's obvious, but you have your f of ht, and then what you're doing is that you're dividing it by delta t.
Yes.
And that's your gt.
Yep. So anyways, it's just a function, what we learn. So this way is I want to reformulate the function in an Euler's fashion. And now we are trying to estimate the function g rather than the original f. So quick review on ODE solver. So what do we have for ODE? Supposing you get a function called h. So h will be a state output from our neural networks. When we have the h will change with the depth of the layers. And we can think this as a kind of gradient field or say vector field. So yes, if we give a derivative about depth, so it's called function g. So g is a derivative function with h with regarding to the t. And it's changing based on your t and the initial value of h. So the goal of having ODE solution here is we'll never give an input ht0, a function g, in time span, and some parameters in the neural networks. We're expecting to give a new state output, which we call ht1. So which means in this field, this is exact track about a continuous function in the h, which will go through from initial value given to the h, which is ht0. And Euler's method is one of the oldest and the simplest way to approximate the h track to the exact function. So the orange line here is actually Euler's method to get the function ht. So a quick quiz. How old is Euler's method? 1600s? So I believe it's older than most of us here. So it's 140 years old. So definitely, it's a very old one. So with respect to its age, we shouldn't have too much requirements on the approximation error. So you still see it's not perfect. And with the modern age, now you see the red line here. This is produced by an adaptive solver, which is called modern ODE solver. So in this paper, the author, they're using the adaptive solver to give this update for the states. Now we can understand the problem is the new state is some output from the black box. And we need to require some input, which is the initial state, and some parameter setting, and your function g. So g can be understood as a simple neural networks, like a part of the structure. So with the ODE solver, you are always to get a continuous track for the whole function. Let's review back to the ResNet. So when we have the ResNet, we need to define what is function g. So you can understand the function g is a kind of a residual networks block. So it's a small block for different layers. Therefore, you have different parameter zeta. So in the function here, the zeta is relevant with the depth. So it's zeta t. So given the function, we're trying to run through each of the depths and updating the state, which is called ht plus 1. And we return the state. So that's how you're looking at it. So you can see like we are due 5 evaluations to the output. So you're getting h0 to the h4. But when we go to the ODE now, what is actually doing? We're still fitting a function g. G can be understood as a small residual networks, small networks. But this time, zeta is no longer relevant with the depth. So zeta is like just a reusable one. So you can always call the g function and put in ODE solver. The good thing for this is like you don't need a for loop. So what you hear is actually you only need to fit the initial state, which is h0. Your function g, a small piece of neural networks. The span of the time and the parameters. That's it. That's the power of the ODE net. And the things like when you see the track, it's more like a continuous and more smooth than the previous ResNet. And the black dot here is actually the evaluation of the dynamics. We say the evaluation is, you can understand like a printout for your function of g. The good thing about ODE net is you are free to do any evaluations you like during the process, as long as you think the htn hit your best desired accuracy. Then you will always feel free to get an evaluation in the whole pre-process. But you have to pay for your evaluation. Because like every time you do some evaluation, it takes a while to get the outputs. So you need to get a trade-off between whether you want to get a good output during the during the whole process, or you want to get an evaluation after a certain period. This is ODE now. Well,
sorry, hold on.
Sure.
I've lost you. So, what is G again?
G is a function. Take this for example. If we are dealing with classification on MNest, so previously when we have the residual nets, G will be a simple neural networks, will be convolution activation thing, but it will be different residual blocks for each of the steps. So you have different data. But for this one, we only need the first residual blocks. So during the ODE training, you only need that small blocks to fit in the model. And you are free to get any HT as you like.
Okay, so what, I guess the part that I missed is what is the relationship between G and the ODE that you're trying to solve? Is that a fair question?
Yes.
Okay.
So back to the problem is like with the ODE solver, we expect several input. The first will be initial value, which is H0. G is a function you need to be put in the solver to trigger your whole solution.
I see. So G is your gradient field, essentially.
Yes, you can understand like that in the neural nets. Yep.
So say you have like a wave
Mm-hmm.
right?
Mm-hmm.
Sorry, that's a comparative. I'm going to simply we do that way. Yeah.
Like later today,
Second half.
not like next week.
Yes. Okay. Should we continue? So the nightmare is actually how you training the beast, because this is a black box. So the awful part is how do you get the gradients for these ODE solver? But initially, just to be relaxed, we're starting with the basic idea to training the model is to get the loss function. And we know the final state HTN will contribute to your loss function. Then you get the gradients, then you update some parameters. To working with this, we replace the loss function to the HTN. It will be a loss function with different ODE solver component. And to getting the gradients is actually to getting these 4 tokens. So these 4 tokens is actually the key to get the updates for the whole ODE net. So we do actually want to say, do not backprop through the whole solver, because it will be a nightmare. Because 2 reasons. First of all, about high memory cost. And second of all, extra numerical error. Because, right, whenever you do something more, you introduce more error. To do this, in the paper, the author recommends using a very special way called a join method to approximate the derivatives. And once you get one adjoint state, then you solve all the 3 tokens. Sure.
What are the parameters of G?
G is a function. G you can understand as a small piece of neural networks. Will be convolution layers plus and then review or other activations.
So it's different from the thetas that you have in your G solver.
It's composed by theta. Yes.
That's why you're not taking the derivatives of L with respect to G, because you're already taking the derivatives of L with respect to theta. Is that correct?
Yeah. Based on the chain rule, you finally need the L to do that. Yes.
Sorry, I thought in this setting, well, there's no concept of layer because all the layers are, combined
Yes.
together as some kind of field.
Yep.
So in this case, of course, backdraw is this one, and because there's no layer, how would you expect the backdraw?
In this setting,
Could
if
you please repeat the question? It's too far away from the mic.
Because
No,
there is no
I'm asking
layer.
the speaker. You're too far.
so, he is asking, because like in this case, there's no actual layers, so will that backprop be useless? in the case. Right? Is that right?
Yes.
Yes. Because like to explain the ODE relation with the ResNet, I do interpret the T as a layers. But actually, we should understand, like, if you take layers as a continuous variable, it then would be a T. So I do still think the T, the backprop works in the T, works in this case, because you can treat your numerals of layers, then which will be treated as T. So the backprop should work with that respect.
So, do you have as many layers for time steps?
For the application in ResNet, like do the classification on MNIST, it doesn't have that numerous number of the layers. But they do have the application on solving the time series model and the continuous flows, which will be a good application for the T. But I do think the backprop should work on both of the case. It's just like different understanding about T.
Yeah, I think the T in the time series one is a different T. It's not the same. Like
Okay.
you can't even, I think you can't, is that right? I think it's a different variable. You can't think of that as the same.
Yes.
So T is the different layers when you're looking at the ResNet, and here there is no concept of separate layers, and that is a different concept. Like I think actually using T is confusing because it makes you think of time, but time doesn't actually make sense
Yes.
there, whereas it does make sense in time series.
But now we can think about this is take the gradient with regarding to the layers, the number of layers. Although like usually in the architectures, it won't be a very infinite number about the layers. Yes.
Sorry, my knowledge to that adaptive solver is relatively poor. So my impression is that, well, discretizing T is equivalent to, well, a conventional, well, residual network with many layers. But in this case, because you're not using a Euler solver, you're using an adaptive solver.
Yes.
And in your previous slide, beads on the curve are like, you know, are definitely not, well, are definitely, it definitely doesn't look like discretization. So maybe, could you spend a bit of time talking about what exactly this adaptive solver is?
You mean here?
Yeah.
So why we still have a continuous track for HE here,
Yeah,
right?
how does it compare to Euler?
So in the neural network, you do see there are only 5 evaluations, like will be the 5 output for different layers. But when you move to the ODE net, it actually, the T can just be understood as a variable. So it will be, you give the initial input, you give a function, then you can just produce any edge with regarding to this variable. And why we have a continuous track here is to better to understand you can do any numbers of evaluations. So whenever you have edge with that regarding to the variables, these are outputs. So you can using these outputs to check if it meets your like a desired accuracy in the classification problem. So this is just a graphical way to think about how to apply ODE neural networks instead of using the ResNet.
Also, you can use a black box solver. That's kind of the idea here. Like your solver is a black box in this context. So that's getting into like adapters versus like Eulers is kind of besides the point.
Yes, but here what you're optimizing is the field itself, if the solver is perfect. So even you have the black box solver, whatever you do, it will be an approximation.
Yes.
So I guess the more proper question is that how do you approximate the field? What kind of, what kind of constraints and regularization do you impose when you insert those beats in some kind of black box where initially you assume you know nothing?
Oh, for this question, I did check their paper. So they tried to using a range CUDA. It's another younger way than Euler's method, but they will get a better approximate to the real track. But in their paper, I do not remember I see how they explain the adaptive solver. They just say this is a black box, but they do see the details about how they do the loss function with regarding to the gradients, but not explained in the adaptive solver. But maybe there's some reference I haven't covered.
Okay, let's move on, please. Thanks.
Okay. So yeah, so last time we're starting here. So we want to get the tokens, like the gradients with regarding to the loss function. And the paper introduced a way to approximate these derivatives. So on the left, with the standard backprop, we can derive these functions. And we did recognize the loss function with regarding to the state is called adjoint sensitivity equations. So it was developed 1960, older than most of us here. I believe. Sorry, I'm using the right one. Anyway, so this is a joint state. So the paper says like how to compute the AT is a function of the loss with regarding to HT. So on the right side. So with the second formula, we do see AT can be solved by another ODE solver. It's like another initial problem. So we can using an auto definition to define the adjoint state. So which is here. To get AT, we're actually solving another initial problem. It's like you need to fit in an ATN. So that's why in the paper we say we actually do the reverse mode. It's like we are tracking back with our output of ATN. Then we get AT0. So the best thing about getting AT0 will be that will solve the rest of the three tokens. Because when you see the loss function with other three parameters, they all have an ATN function. So when you solve these gradients, you're calling another ODE solver, give you the AT. And the rest of the piece will be just trained during the whole, will be trained and will be the output as a regular neural nets. So the best way about the greatest idea in this paper is they're introducing a modern way to using the adjoint state to solving this framework. So overall, when you're using a package, it doesn't need to worry about how you get these four tokens with regard to the loss function. What you need to fit is the HT0, the G function, and that's it. So whenever you trigger that black box, they will call another black box to help you find the token for AT. Then you will get the whole pre-process. So it will be here. Like here. So we fill in AT0. And you can understand G as a simple neural networks and initial state. And that's it. And now we are come to the breakpoint. And after the breakpoint, we want to see the application about ODE solver on a supervised learning. Because there are two other applications in the paper. And will be about applied ODE nets to solving the time series problem and normalizing flow problem. But because my knowledge in the time, I didn't want to go further that yet. But we are going to see the application about replace the ResNet with our ODE nets and the performance and the benefits of the ODE net.